Hello, everyone. I'm happy to give the second in the head talk of this workshop. So this is spatial computation in the head. This is a joint work with Thibaut Feneuil, who is here. And so the scope is two papers. So one that was published at Asia Crypt, and a follow-up work in which we improve this spatial computation in the head framework. So this is a framework of MPC in the head, where we propose to apply threshold secret sharing to the context of MPC in the head, and in particular, Charmier secret sharing. Okay, so this is the roadmap of my talk. So first, I will give an introduction on MPC in the head. Then I will describe this framework and some application to post-quantum signatures. So we will see first a variant using Merkle trees for commitments. Then a second variant using GGM trees. Then we'll see how we can use some features of Charmier secret sharing, so namely the multiplication homomorphism and the ability to pack secret sharings. And then I will present a specific application of the framework to construct post-quantum ring signatures. And finally, I will conclude by discussing some relation with other proof systems, and in particular with Vol in the head that was presented yesterday. Okay, so the MPC in the head paradigm to build the signature scheme can be seen as a four-step process. So in a first step, you would pick your favorite one-way function. So for instance, that could be AES or MQ system or a syndrome decoding system. So this one-way function will be denoted F. And then you pick a random secret input of this one-way function, X. And the corresponding output, Y, is public and will be the public key. So X will be the secret key, Y will be the public key. So then in the second step, you would design an MPC protocol in which some parties receive a secret sharing of X, and they will jointly compute the function G of X, which output accept if X is the correct preimage of the public Y, and that outputs reject otherwise. Then the third step is to turn this MPC protocol into an interactive zero-knowledge proof. So in such a proof, a prover will prove to a verifier the knowledge of the secret X that correspond to the public Y. And then this can be turned into a signature scheme using the Fiat-Charmier transform. Okay, so the MPC in the head transform is this step in the middle that goes from the MPC protocol to the zero-knowledge proof. And we will focus on this now. Okay, so first, I'd like to say a word on the MPC model that we consider to construct those proof systems. We will consider a linear secret sharing of the secret input X. The parties jointly compute this function, which validate that X is a correct witness. So that output accept is X is a correct preimage of the public Y and reject otherwise. We'll assume that this protocol is L private, meaning that we can fully reveal L parties without compromising the secrecy of X, and that it is secure in the semi-honest model, which means that we don't require active security for this MPC protocol. And in addition, we also consider protocols in a broadcast model. So that's a model in which the parties will locally compute under shares and broadcast the result of the computation, so that the broadcast sharings can be publicly recomputed. So we can recompute publicly the value corresponding to the broadcast sharing. And this value can then be input in subsequent rounds of the computation, of the MPC computation. So that's the basic model we use here. Yeah, by the way, feel free to interrupt at any point if something is not clear. Okay, so let's see how we can transform such a MPC protocol into zero-knowledge proof, interactive zero-knowledge proofs, using the MPC in the head transform. So first, we will generate and commit a secret sharing of X. So meaning that each share will be committed separately. So we have one commitment per share, and the commitments are sent to the verifier. Then the prover will run the MPC computation in their head, meaning that they will compute all the broadcast messages of all the parties, and they will send those broadcast messages to the verifier. Then the verifier will select a random set of L parties. So L is the privacy parameter. So the verifier will challenge the prover to reveal those L parties. And the prover will reveal those parties, so meaning that they will send the corresponding shares to the verifier. And finally, the verifier can, based on those open parties, can verify that the commitments were correct for those parties, can recompute the MPC computation for those parties and check that the broadcast messages were correct as well. And also check that the broadcast messages lead to an accept of the protocol. Okay, and yeah, and that's it. And so the soundness of the proof comes from the fact that if the prover is malicious and doesn't know a correct X, a correct preimage of Y, the prover would have to cheat for some of the parties and would have a probability to be discovered by the verifier. Okay, so now we'll see what I will call the traditional setting of MPC in the head, how it works with, in particular, with additive secret sharing. When we use additive secret sharing, we will randomly generate n-1 of the shares and compute the last one. So basically, we will randomly generate all the shares and correct the last one so that all the shares sum up into X. And usually this is done, so since a paper introduced this technique in 2018, we do that using a GGM tree. So that's a seed tree where we generate a root seed, and then this root seed is expanded using a binary tree structure. And at the bottom, we have the leaf seeds. So we have one leaf seed per party, and this leaf seed is used to pseudo-randomly generate the associated share. Okay. And we have here this correction value, which is added to the last share to correct, and so that it is a correct sharing of X. Okay, so this technique is interesting in terms of communication, so we'll see why in a minute. And yeah, so we have that such an additive sharing is n-1 private, meaning that we can reveal n-1 shares without revealing the secret. So let's assume that we'll use MPC protocol that preserve this n-1 privacy. Then the verifier will ask to open n-1 party, so only one party remains hidden. And this implies that we obtain a soundness error of 1/n for the proof, because the malicious prover would have to cheat for at least one party, and then the probability of not being discovered is of 1/n. Okay. So that's the soundness of the scheme, and we can, of course, repeat this protocol in parallel several times in order to amplify the soundness and get the target security. Okay, so when the prover is asked to reveal n-1 parties, instead of sending n-1 shares or n-1 seed used to generate those shares, they can only reveal a logarithmic number of parties. This is due to the structure of the field. And that's because here, so if the second shares remain secret, we have this pass from the root seed to the second leaf seed that must remain secret. But we can reveal all the other seeds by revealing the seeds on the sibling path here. And this is, yeah, logarithmic in n. Okay, so now we'll see how we can use chamois secret sharing in this setting, and yeah, we'll first look at the Merkle-Tree variant of the scheme. Okay, so here now we want to generate a chamois secret sharing of X. So such a sharing is defined with respect to a polynomial P. So this is a random polynomial that has X as constant term. and which is of degree L, and the L coefficients here are random. And so then each share xi is computed by evaluating this polynomial in a fixed point ei over the field. Okay, so it's well known that this sharing is L private, meaning that we can reveal any set of L shares without revealing any information of X. If we reveal L plus 1 shares, then we reveal the full sharing. And in our context, we will use a L, which is small compared to N. So that means that there won't be a lot of randomness in the sharing, but there will be a lot of redundancy. Okay, so because of this redundancy and this not a lot of randomness, at a first sight, we cannot use a GGM tree to commit such a sharing, generate and commit such a sharing. So we'll just commit the generate the sharing randomly, following the procedure I just showed. And then each share will be committed using a Merkle tree. So each share will be hashed and become a leaf in a Merkle tree. And yeah, so this is well known, hash tree. And then the root of the tree will be used as global commitment for the sharing. So we send the root of the tree to the verifier. Okay, so then, so once again, L will be small. So for instance, L could be equals to 1. And in that case, we'll have the verifier asking the prover to reveal a single party. So we could think that this would lead to a bad soundness because we could think that the verifier, the prover, sorry, would have a lot of opportunities to cheat. So they could cheat in any of the hidden party, right? This, in analogy with the previous setting, we would get a soundness error of n minus L over n, which is pretty large. But actually, the situation is better because the broadcast messages must correspond to a Shamir secret sharing. So the verifier will additionally verify that the broadcast sharings correspond to correct Shamir secret sharing, so with a lot of redundancy. And this will reduce the ability of the prover to cheat. So I won't explain this into details. You'll have to trust me or to read the paper. But we obtain a soundness error which is much better, and which is of 1 over this binomial coefficient of L amongst n. And yeah, so for L equal to 1, we recover the 1 over n as in the additive case. Okay, and then in terms of communication to open the sharing, we still have something logarithmic because we reveal not a sibling pass in a seed tree anymore, but an authentication pass in a Merkle tree, which is also logarithmic. And yeah, so that enables the verifier to check that the revealed share indeed correspond to the Merkle root that was committed in the first place. Okay, so now I want to add some additional aspect about the soundness, which is that in practice we don't use we use MPC protocols that are probabilistic. So in practice, those protocols might have what we call false positive, and sometimes accept a sharing X for which X is not a correct preimage of Y. And yeah, that's so in the model, we also have that the parties have a source of randomness. And in the MPC, in the head setting, this source of randomness is challenged sent by the verifier. And then, yes, depending on the randomness, we can have such a false positive. So we did not P this false positive probability. And in the standard setting, so when we have such false positive, the soundness is actually 1 over n plus P. So the hope here would be to have this fraction with this binomial coefficient and with this additional P. But in practice, this is not what we get. we get that this false positive is multiplied by a factor depending on n and L. So for instance, for L equals 1, this factor is about n over 2. And if this false positive is not negligible, then this factor might actually degrade the soundness. It's not an issue if the false positive is really small, but if it's not, then we have a soundness degradation. Okay, so why do we have this? I'll try to give not a formal proof, but some insight about what we have this. And that's because the prover can commit invalid Charmy secret chaining. So with the Merkle commitment, nothing prevents the prover to generate some arbitrary sharing, which is not actually a Charmy secret sharing corresponding to a polynomial of degree L. And so doing so, if we consider the sharing that we will interpolate for some set of party J, for different set of parties, we could have different sharings and different X, and each X would lead to a different false positive, corresponding to different randomness from the verifier. So that's why we get this factor. That's because there is much more opportunity of false positive for the malicious prover. And so a solution to this issue is to use what we call a degree enforcing commitment scheme. So we add one round of iteration at the beginning when we commit the sharings. And we use a technique that is inspired from Ligero, and which is that the verifier will send some random coefficient, and the prover will respond with some linear combination of the shares corresponding to those coefficients. And then the verifier can check that those linear combinations are indeed of the right degree, and with high probability, this implies that the shares were of the right degree in the first place. So we do that before the MPC computation. It's a bit different to what Ligero does. And this enabled to retrieve this target soundness that we hoped in the first place. Okay, so now I'd like to give a comparison between TC in the head with this Merkle tree commitment and the standard setting of MPC in the head. So I will use a parameter degree for the polynomial L equals to 1, because we get the same soundness for the two setting with L equals 1, so we get a fair comparison. Okay, so for the standard MPC in the head, I'm assuming so that we use seed trees as presented, and that we use the hypercube technique, which is a technique that was proposed at Eurocrypt last year. And so this technique enabled to reduce the number of party emulation done by a prover from n to log n plus 1. Okay, so compared to this improvement, we further improve this because we obtain only 2 party emulation. And to see why, that's because so with L equals 1, any 2 shares define all the shares. So any 2 party computation define all the other party computations. In terms of symmetric crypto, for the prover, it's in both cases it's linear in n. So whether to construct a GGM tree or Merkle tree is linear in n. Then for the verifier, we have 1 less party emulation in both cases, so log n versus 1. But in terms of symmetric crypto, it's much better with Merkle tree because that's verifying an authentication path in a Merkle tree, which is logarithmic, compared to reconstructing a GGM tree, almost a full GGM tree, -1 pass, which is still linear in n.
Just a quick question. So when you mentioned taking L equal 1, so in the previous slide, it looks like an optimal choice for the soundness would be to take like L equal n divided by 2. So why do you prefer to take L equal 1?
Yeah, so that's because so if you increase L, you also increase the number of authentication paths you must put in the signature, and also the number of shares you must reveal. So if you look at the trade-off, it's not always interesting to increase L. Taking L equals 1 can be more interesting. It's a trade-off. There is some context where it's more interesting, but it's not groundbreaking anyway, because you will compared to having further iteration of the proof system, if you increase L, so yeah, you would like double the bit of security that, so going from L equals 1 to L equals 2, you would double the bit of security of the soundness, but you can do that with one more iteration as well, right? And so one more iteration, it's also one more pass in the tree, one more share you reveal. And so, yeah, so, and it's not actually doubling because it's not squared, but it's a binomial coefficient. So, yeah. But in some context, it's still interesting to increase L. It depends of the implicit protocol, basically.
Thank you.
Welcome. Yeah, so then we also have some downside by using this Merkle tree commitment, which is that the size of the tree is doubled. And that's because, so in a sibling pass composed of seed, we have log n seeds of lambda bits, where lambda is a security parameter. But in an authentication pass, we have lambda digest of size 2 lambda bits. So the size of the tree is basically doubled. And for 128 bits of security, we go from 2 kilobytes for approximately 2 kilobytes for GGM3 to 4 kilobytes for Merkle tree. And the second downside is that we are limited with the number of parties, since so the number of parties is at most the size of the field, since we need 1 point of evaluation per party using a Shamir scripture. Okay, so now I'm going to present a second variant of this framework where we actually use GGM trees, and yeah, that enable to get rid of those two limitations. Okay, so to use GGM tree to generate and commit Shamir secret sharing, so we have two steps. So in the first step, we simply generate a random seed tree. So now I will denote each additive share generated this way by Ri, so R1 to Rn. So here we still have an additive sharing of X, but we won't distribute one additive share per party. What we're going to do is to distribute all the shares but one to each party. So the first party will get all the randoms but R1, second party all the randoms but R2, and so on. And so that's called a replicated secret sharing. And the second step, we'll use a technique from a paper of 2005 to convert this replicated secret sharing into a Shamir secret sharing. So to do so, we'll define the polynomial P of the Shamir secret sharing as follows. So it is delta X. So delta X is the correction value, plus the sum of the Rj times Pj, where Pj is a polynomial which evaluated in 0 equals 1 and evaluated in the point Ej equals 0. And so using this, we can check that we obtain a correct sharing of X, because if we evaluate P in 0, we recover delta X plus the sum of all the randoms, which is X. And we also have the nice property that the party I can compute the share Xi, because Pi will vanish, and so we don't need Ri to compute the share Xi. So actually, each party can compute the associated share with all the random, but the random of corresponding index. And then if we want to reveal a single party, so if L equals 1, we want to reveal a single party, then we will just hide one random, which is the random. So if we want to reveal party 2, we hide random R2. And this is done as in the additive secret sharing case with the GGM tree, where we keep the pass hidden and reveal the sibling pass. So this technique can also be adapted to a degree of sharing greater than 1. So now we have the size of the GGM tree, which is nice. We also have a good soundness. So we don't have this issue with the factor on the false positive probability. And that's because by construction, we commit correct Shamir secret sharing with this technique. But unfortunately, we lose the fast verification of the GGM tree. Okay, so this is actually close to previous MPC in the head using additive secret sharing. We support exactly the same type of MPC protocols. We have the computation of the GGM tree, but we have just reduced the number of party emulation. So if with the traditional approach, there was n party emulation, with the hypercube, it's 1 plus log n. And with this technique, it's only 2 party emulation. But actually, we still have the, I didn't address this issue of the number of parties that must be smaller than the field. And for this, we have a trade-off where the number of party emulation is actually 1 plus log n over log f. And so this means that if the field is large enough, we obtain 2 party emulation. If the field is the smallest, f2, we obtain 1 plus log n as for hypercube. And yeah, in the middle, we obtain some trade-off better than hypercube, but more than 2 party emulation. Okay, so to give an idea of the kind of saving we can obtain using this technique instead of previous MPC in the head techniques. So we've applied it to the candidates of the current NIST MPC NIST call, so the candidates which are based on MPC in the head. And so we obtained, so we did that using a generic MPC in the head library, so to get a fair comparison. So, and yeah, but for the MPC part, we fetched the code from the submission package. So we see that we obtain different improvements. So we obtain 0 improvement compared to hypercube for the schemes that are on F2. But for the others, we obtain some improvements, so ranging from yeah, around 15% and up to 50%. Okay, so now we'll see how we can use further feature from the Shamir secret sharing to even improve this framework. Okay, so it's well known that Shamir secret sharing has this multiplication homomorphism. So if I multiply 2 shares of X and Y, I will obtain a sharing of the product. But if the original polynomials were of degree D, then the output polynomial is of degree 2D. And using this homomorphism, we can build a simple protocol to verify polynomial constraints. So assume that we can check the validity of our witness W by applying some polynomial to W and checking that we obtain 0. So we have m such polynomial, f1 to fm. Then we can define a simple MPC protocol that computes such a sharing alpha, which is broadcasted. And this sharing should be a sharing of 0. And so to do that, we'll ask some randomness from the verifier. Then the party will locally yeah, I think the pointer is out of battery. Ah, no, okay. Yeah. So yeah, so the party will locally compute the polynomial applied to the witness, and they can do that thanks to the multiplication homomorphism. Then aggregate all those into using the randomness from the verifier. So if we have a valid witness, those fj apply to this sharing should be sharings of 0. And this aggregation should be a sharing of 0. And they will also add some pre-committed sharing of 0 in order to hide high degree coefficients here that could reveal information. And broadcast that, and the verifier can just check that we have this alpha is a sharing of 0. And here we have a false positive probability of 1/f, which is due to this way of aggregating the constraints. And of course, we can do that. We can compute several such alpha sharing if we want to increase, to decrease this false positive probability. Okay, so now in presence of such a scheme with higher degree MPC computation, the one that we had here before above the fraction is replaced by another binomial coefficient, which is L, the degree of the initial sharing, among d alpha, where d alpha is the degree of the sharing corresponding to alpha, the alpha sharing. And so here, with this protocol, we'll have that this degree d alpha is L, the degree of W, times the degree of the polynomial constraints. Okay, so here we have a degradation of the soundness. But if n is still big compared to this L times the degree of the MPC computation, we still have a good soundness. Okay, so we've applied this approach to the different candidates based on MPC in the head of the new NIST goal. So we applied such a protocol to the instances of the problems considered by these candidates and tweak the MPC computation to use this simple MPC protocol. And we could obtain some saving in the size, ranging from 5 to a lot of around 50% and even to 30%. So we see that we obtain good improvement for MQ because MQ is the perfect statement for this type of protocols. We also applied to other instances of MQ and syndrome decoding and obtain even greater improvements. And so that's those numbers. So those are for the signature size with 256 number of parties. If we use 248, so now that we reduce the number of party emulation, we can increase the number of party and remain efficient. Then we obtain those sizes, and we see that we get closer and closer to something like 4 kilobytes, sometimes a bit above, a bit lower, from which 2 kilobytes are the symmetric part, the GGM tree. So we're really squeezing the MPC computation with this kind of techniques and get something where the different assumptions and different statements are more and more competitive. Yes, you had a question?
How does it affect the signing time? Or does it?
This technique?
Yeah.
So yeah, that's a good question. I don't have numbers here, but it doesn't like affect a lot the signing time. Okay, so I'd like to mention two recent works. So there is this paper, One Tree Rule Them All, that was covered in the presentation of Carsten yesterday. So that proposed some generic techniques to reduce the size of commitments with GGM trees. And yeah, I just want to mention that we can also use this kind of techniques here, or with standard MPC in the head. And this would like basically reduce the size of the signatures I showed in the previous slide by about half a kilobyte for 108 bits of security. And there is also this work where we propose some new protocols for min rank and rank syndrome decoding problems, which take advantage of this type of protocols and also obtain better sizes. Okay, so now let's turn to the second feature we can exploit with, yes.
Hi, sorry, I just wanted to ask a quick question. In the previous slide, with your results, why did aim and write not benefit from why did they not get any savings? I think the number slide before this with aim on it, aimer.
Okay. Here.
Yeah. Aim and ride.
So aimer and ride. So the saving are between hypercube and TC in the head, and aimer and ride are on the field F2. So here we basically have 1 plus log n for those schemes, and so no saving compared to hypercube.
Okay, thank you.
Okay, so it is known that we can pack several values into a Shamir secret sharing. So this goes as follows. So assume we have a vector with s coordinates, x1 to xs. So what we'll do is to define those coordinates as evaluation of the underlying polynomials. Then we pick L random values, which are L further evaluations. So we obtain a polynomial P of degree s plus L minus 1. And so we interpolate this polynomial from the secret and the randomness, and we apply this polynomial into fixed points, which must be different evaluation points than the one that we use for secret and randomness. And yeah, that worked this way. And then if we add to sharing this amount to adding the underlying secret vectors, and if we multiply to sharings, this amount to multiply the vectors coordinate-wise. And so using this, we can use MPC computation that do like kind of parallel computation. Then in terms of soundness error, we still have this, but here the degree of the broadcast shares is impacted by this increase of the degree of the original sharing. So we'll have that instead of L, we have L plus S minus 1 multiplied by the degree of the MPC computation. So so we'll have a degradation of the soundness. But on the other hand, we can divide the size of the witness by a factor S, and that's only if we use Merkle tree commitments, because if we use GGM tree, we have to communicate the correction value for the sharing. And even if we use pack secret sharing, we still have to communicate correction value, which is the size of the full witness. Whereas with Merkle trees, we will still open only L shares and communicate L shares, whatever the packing parameter S. So that's why pack secret sharing is interesting with Merkle trees, but not with GGM tree. And since we have this degradation of the soundness, it's basically a trade-off. So using packing will be interesting, but not for very small witnesses, but for what we call medium-sized witnesses. And I don't have a precise definition of that, but yeah, that's just to give the feeling that we have a trade-off between the two approaches. One context in which it's interesting to use Merkle tree with packing is for a zero-knowledge proof of a lattice statement. So for instance, an ISIS or a CIS or LW statement. And where we want to prove a knowledge of a small vector E, I mean a vector of small norm, because actually the vector is not small, there are a lot of coordinates, and for this type of statement, it's better to use Merkle tree with packing. And we actually obtain sizes which are competitive with the state of.
Matthieu, can I ask a question?
Yeah.
So for the norm, can you use two norms, or is it really designated to the infinity norm?
So we can use infinity, we can use L2, we can use, I mean, if we want to prove something about L2, we will prove something about infinity norm. That's how. Actually, we could prove, in addition to infinity, we could prove L2. It won't be expensive to do that in addition, but to prove L2, we would go through infinity norm.
Okay.
With the technique we use.
I see. Thank you.
Okay, so just to give a high-level comparison between the two variants. So with GGM, we have smaller trees, but we don't have the ability of using pack secret sharing to reduce the witness size. With DGM, we have a naturally enforcing of the degree of the committed sharing, which is not the case with Merkle tree. With Merkle tree, either the false positive is small, very small, or we have to add this degree enforcing commitment scheme, which is an additional round with additional communication. And yeah, just to repeat and to conclude about this high-level comparison, DGM tree variant will be better for very small size statement, such as those we have to construct post-quantum signature where we care for very small size of signature. And Merkle tree are better for medium-sized statement that could be, for instance, lattice proof system or general zero-knowledge arguments for arithmetic secret of medium size. Okay, so I don't know. Okay. So now I'd like to focus on a particular application of this framework, which is to construct post-quantum ring signatures. Okay, so just to recall in the standard setting, what we have, so we have a secret key, so which is not denoted W, a one-way function F, a public key Y, which is F evaluated into W. We use the MPC protocol that verify that sharing of W correspond to the public Y. And using the TC in the head framework and Piachamir, we can compile this into a signature scheme. If we want a ring signature, so that's a signature scheme where we have a ring of user, and a user can sign a message, which the verifier can be convinced that it corresponds to a correct user in the ring without knowing which user it was. So now we have R, so R is the size of the ring. We have R secret keys, R public keys. And we want an MPC protocol that, so denoted pi prime, that will take a sharing of one of the correct witness, one of the secret keys, a sharing of the corresponding secret index, and check that this is a valid witness for a public key in the ring corresponding to this secret index. Okay, so that's the general approach we propose to construct a ring signature using TC in the head. And so yes, if we compile this now with TC in the head and Piachamir, we obtain a ring signature. Okay, so the idea is to use a one-hot encoding of the secret index J star. So this is a vector with all coordinates equals to 0, but the correct coordinates to index J star equals to 1. And so this protocol pi prime shall first compute sharing of the correct public key by aggregating all the public keys with this with the sharing of this one-hot encoding. Okay, so this is just linear computation between the shares of the one-hot encoding and the public keys. The problem with this approach is that we don't want to include the sharing of this one-hot encoding to the witness because its size is the size of the ring. So that would lead to a signature increase by the size of the ring. So the solution we propose is to use a kind of d-dimensional one-hot encoding where we have d small one-hot encodings, and which are such that if we compute their tensor product, we recover the global one-hot encoding. So those are small vector. You can think of vector of size 2, for instance, with one coordinate to 1, one coordinate to 0. And if we compute the tensor product of that, we recover one-hot encoding with a single coordinate to 1. Okay, so if this d parameter is log r, then the size of those vectors is 2. And then now we increase the size of the signature only with log r. Okay, so let's look at this full protocol pi prime. So we have the witness, which is one secret key in the ring. Those small one-hot encodings. So first we'll compute the global one-hot encoding by tensor product between the small one-hot encodings. So we can do that because we have the multiplication homomorphism. So this is a degree d-1 computation. Then we compute the sharing of the correct public key in the ring, as we just saw. Then we will use the original protocol pi to check that the witness is the correct witness corresponding to this public key. And finally, we have another step which will check that the sharing of S is indeed a sharing of a one-hot encoding, namely of a vector with only 0 coordinate, but 1 to 1. So for this last step, we propose a simple MPC protocol, which I don't detail here for the sake of time, but it's simple and efficient. And yeah, we must adapt the protocol, the initial protocol pi, because now we don't have a public key, which is public. We have a sharing of the public key. And this sharing is of high degree. So yeah, we need to adapt that. We have increased the degree of sharings. But yeah, but it works. And actually, we'll see in the next slide, the size are not too bad. So yeah, that's the solution. And yeah, now if we compile that with TC in the head and Piachamir, we obtain ring signatures. And so this is a general approach that can be applied to any type of statement with existing efficient MPC protocol. Okay, so we've applied this approach to different assumptions, so MQ, syndrome decoding, and AES. And so we obtain some sizes ranging from 5 to 13 kilobytes for a ring of size 2 to the 20, which is interesting compared to previous works, where for a ring of size 2 to the 10, we have greater signature sizes and sometimes much greater. And also for those previous work, there were usually no or slow implementations, whereas we provide some implementation for the MQ and SD variant. And those implementations are fairly efficient. So for rings of size 2 to the 10, we are smaller than 10 milliseconds. Then it increases. Okay, so we get 100 milliseconds for rings of size around 2 to the 15. And yeah, then we still have the running time is linear in the size of the ring. It's because we do linear computations inside of the ring. So yeah, but those are not highly optimized implementation. Maybe we could optimize more. Yeah, that's still fairly efficient. Okay, so I'd like to conclude by discussing some historical aspect of our work and relation to other proof systems. So the initial motivation was to study the application of Shamir secret sharing to MPC in the head. And that led to our first work where we consider Merkle trees. Then in our later work, we proposed this GGM variant, the use of pack secret sharing, nonlinear MPC computation, and degree enforcing commitment scheme for Merkle tree. And actually, this framework, those variants are connected to other proof systems. So the GGM variant is actually very close to vol in the head. We kind of rediscovered vol in the head with another pass. And to see this, if you take a Shamir secret sharing of degree 1, but you put the secret in the leading coefficient, then you get something which is as a vol correlation that was presented yesterday. And with this GGM3 variant, it's actually similar to what is done with vol in the head. But vol in the head also use an additional ingredient, which is a large feed embedding. So it can reduce slightly the size of the signature. On the other hand, it implies some multiplication in some larger extension field. So yeah, using this might provide a trade-off. So in some cases, it might be giving computation, in other it's not. And we also have that, yeah, we could increase the degree of the Shamir secret sharing, which is not part of ball in the head, and that could be interesting in some use case. If we look at the Merkle tree variant, then it's closer to another type of proof system, which is Ligero. And actually, if we use this variant with a specific protocol, which was proposed in Ligero, we get something that is very close to the Ligero proof system, but with some concrete improvements, in particular due to this degree enforcing commitment scheme we proposed. And yeah, we obtain like some improvement of the size by a factor like something like 2, let's say. Yeah, so this framework can of unify different approach, MPC in the head, ball in the head, Ligero, and yeah, might provide insights for further construction in the future. So with that, that's the end of my talk. Thank you very much for listening to me.
Thank you, Matthieu. Do we have any questions?
Thanks for the talk. So I was wondering concerning standard digital signatures, do response sizes vary a lot depending on the challenge, or they are pretty much the same for all challenges? I guess that this question just applies to the case L bigger than 1, because otherwise, I guess.
No, the response size is basically the same. It can vary if, so basically, you know that you have, for one part, so in the standard setting of additive secret sharing, you have this correction value, which is added to the last share. So if the last share is the one that is not revealed, you might not communicate this correction value. But it's just a factor 1/n. And sometimes for the simplicity of the implementation, you might just always communicate this correction value. So, and we have similar things with TC in the head and GGM3. And with Merkle tree, it's always the same. Yeah, right. So that's with the response of the shares. Then what can vary is also, for instance, with the Merkle tree, if L is greater than 1, you have several paths in the tree. So those paths might be more or less common. So that might also vary a bit.
But I guess that there isn't like one challenge for which you have the most unfortunate.
It's very balanced, yeah.
Thanks.
Any other questions?
Thanks again for the talk. Could you say something about how the size of the proofs for exact lattice statements scales with the length of the witness?
Sorry?
So you made this comparison to other proof systems for proving lattice statements, in particular exact proofs. Could you say something about how the size of those proofs scales with the length of the witness, the length of the secret vector that you're proving?
Yeah, sure. So it's sublinear, basically. So when you use pack secret sharing, you obtain arguments which are sublinear. So like in Ligero, for instance. So that would, yeah. Basically, Ligero is like in square root of the set of the witness. With our tweak, it's asymptotically not as good, but better for small sizes, basically, small, medium sizes.
Okay.
So at the end of your talk, you showed how like you have a general framework that covers a lot of type of proof systems. Did you try playing around with other type of secret sharing, like Chinese remainder theorem based ones, or like the one by Blakely and Meadows, like all this like a bit more niche secret sharing?
Not so much. We tried to investigate during our first work if we could use some other type of secret sharing, of threshold secret sharing, to get more parties, actually, not being limited. But yeah, the one we investigated didn't give good result for this purpose. But yeah, we didn't investigate much more different type of secret sharing.
Any other questions? Okay, if not, then let's thank Matthieu again.
Thank you.